welcome back to Introduction to Computer Networks at NTU. Yeah, this is the Wednesday session, so if you look at the announcement, nothing new really, except that later today at 1 p.m. you will see the exam results. So take things easy. Most of you did really well, and some of you might feel that it's lower than expected. It's okay. There's another chance, exam 3, to try to make up. And good morning to you all, including Ivan and James. Okay, and I have a special thanks to say today because there's a construction upstairs on the 6th and the 7th floor of the Berryland building, and I'm right below the construction. And so the workers there are really kind. They will try to shift the work and not doing any of the drillings that's making big noises this morning. Okay, so guys, thank you. Say thank you to the construction workers, please. All right, so Polly first. Wait, thank you. All right, yeah, same. And good morning, Paul and Kelvin. Yeah, thank you to the construction workers. All right, and they're really nice. They're really nice. And so let's go ahead and start with the topics today. Today is going to be all about Chapter 5. In fact, next week is also Chapter 5. So the first video is to break the sections in Chapter 5, and Polly telling you which section we'll be spending a lot more time on and which sections we'll skip because there's nothing really technical. Chapter 5, Network Layer, the Control Plane. Control plane is also what Polly likes to joke about, the better half of the data plane. Now the reason for that is this. If you think about data plane, that forwarding function there, what it does is simply, right, for each incoming packet, do a table lookup, and you know what to do with the packet. Okay, so for each incoming packet, one table lookup, and that's it. There's nothing really intelligent about it, right? The only thing the forwarding is doing just table lookup, and it's just pattern matching, right? But hey, we are sending all sorts of packets coming from different sources, and they're going to different destinations, right? You cannot be sending these packets to arbitrary directions and hope that they will reach the destination. No. So that table there is really where the intelligence is. That is really, okay, guiding the packets to go to the right direction, eventually reaching the destination. So the data plane, the forwarding function, although very busy, working tirelessly, trying to forward packets, okay, but it's actually simple, stupid. Intelligence is right here in the control plane, and the intelligence is implemented using these, the routing algorithms. Okay, so routing here, what I meant as a function is to find a path, okay, for a particular source to be able to send packets to a particular destination, or to find a path so that packets belonging to a flow can flow through the network, okay, with the right amount of resources reserved. Okay, so routing algorithm there, very intelligent. Okay, so in fact, the first part of Chapter 5 is going to sound a little bit like you're attending an algorithm course. So Polly will be speaking about two general routing algorithms. Okay, so they are graph algorithms. So provided a graph, okay, if you think about it, a network having machines connected by cables is a graph, right? Points connected by lines. So provided a graph, we could calculate, we could compute the shortest path from one arbitrary point to another point. So that is what the magic of the routing algorithms are. So these two general routing algorithms will be implemented on the internet as two routing protocols, OSPF and BGP. We'll talk about these routing protocols later after we finish describing the general algorithm. Now these routing protocols are running on the traditional routers, where you have the data plane and the control plane. So the routing algorithm is running in the control plane. Okay? The control plane of each router might be communicating with the control plane of other routers, and together they complete the task of calculating routes, and in turn generating the forwarding table, and in turn install the forwarding table to the data plane, and in turn the forwarding function, okay, can be working really fast. Now, the new model of doing routing is called SDN, software-defined networking. So the one that's doing the route computation is the controller. Okay, this is also known as the what? Remote controller, because in SDN, okay, the model is slightly different. You still have the data plane doing the forwarding, but the control plane is implemented outside of the routers. Okay? In fact, powerful machines, somewhere remote. That's why these controllers are also called the remote controllers. And between the remote controllers, routing, okay, is being done where we generate the flow tables. And the CA, the control agent, now in the data plane, okay, that's taking in all these tables being transferred from the remote controller. Okay, in between, there's this open flow protocol. Okay, now you should know after chapter 4. So after the control agent receiving the flow table, the flow table gets installed, and therefore the SDN routers can do flow table lookup, okay, do generalized forwarding. Now, the remote controller here, okay, it's actually quite general. Inside the remote controller, you could implement multiple routing algorithms, such as the one used by the traditional routing. You can also implement other routing algorithms, and in addition to all these routing algorithms that could be running simultaneously, and you pick and choose a particular route for a particular pair of source and destination. You could also actually specify preferences, or specify costs, okay, or specify other functions. Okay, so SDN's remote controller, being very general, okay, is actually working like pretty much a regular computer, okay, or expensive servers. So on these SDN remote controller, okay, we run operating systems, elaborated operating systems, such as ODL or ONOS. Okay, so these are two different operating system architectures, and both have big camps of supporters. So yeah, SDN routers are made available today that both operating systems can be installed, okay, to support route computation, flexible route generation, flexible flow table generation. Okay, so these protocols, as well as these two, okay, of the technical components in chapter 5 concern the routing function, the second important function in the network layer. In the control plane, okay, we also implement some protocols that is to do this, the management, okay, so management of the routers or the routes or the packets traveling certain routes. Okay, so those are called the ICMP. So ICMP there is to allow generation of special messages from the routers or from the host to the routers, and routers generating something back. So these are there for the network admin to sort of probe the network to find out, okay, where and what might be going wrong inside the network. SNMP. Okay, so SNMP there, the management protocol is more there continuously tracking, okay, the statistics of the network. For example, number of packets traversing a router, number of packets traversing a route, okay, number of routes on a router, and things like that. So that the network admin can know better the status of the routers, status of the routes. Okay, so again, for management purpose.
Yeah, a lot of new terms, but no worries. For the new ones, we'll talk more about later this week and next week. Now, the second video is still chapter 5 overview, but it works really more like a review because we are in the network layer. So there's the separation of control plane and data plane, right? So chapter 4 is the data plane that talks about forwarding. Chapter 5 is about the control plane that talks about routing. And you know what? Routing, very similar to forwarding, there's a traditional version of it and there's a more modern version of it. Traditional one, more specific algorithm. The modern ones are more general. You can use potentially one algorithm at one particular time, or sometimes a combination of the algorithms. Okay, so separation of the planes and traditional routing versus the modern day routing or the SDN routing.
Let's go real fast through 5.1, the introduction. Again, network layer, we run two major functions, forwarding and routing. Forwarding is about moving packets real fast from one router to another. Routing, however, is for each router to generate this forwarding table or flow table, or to determine the routes for the packets to move, okay, from one to another router. So, in chapter 5, we focus on the control plane here. The two models, okay, for route computation are these, the traditional routing versus the SDN routing. In the traditional routing, each router implements part of these routing algorithms, and so the route computation is somewhat distributed, and the routers work collaboratively to come up with the best routes. Okay. So there's per router control plane doing the route computation. But in SDN, okay, the route computation is more centralized, running on powerful machines, and also somewhat distant from the physical routers. So centrally controlled, and this control is called the remote controller, as they are being physically distant from the router. More specifically, in traditional routing,
Okay, the routing algorithm is implemented and running on each of these routers, and they'll be interacting with each other to generate the best routes, therefore coming up with the forwarding tables. Okay, so in the data plane, yeah, there's this forwarding table in the data plane. The control plane there runs the routing algorithm, and together they generate the forwarding table and forward it and installed in the data plane. Now, the modern routing, the SDN routing, works this way. Okay? There's going to be a remote controller there, okay, doing all the computation and then interacting with the local control agent to install these forwarding tables, or more precisely, flow tables. So router, yeah, data plane here, having these control agent, and then at the control plane, we have powerful machines running the remote controller. Remote controller interacting with the CA, setting up these flow tables.
So once again, the control plane in modern days are more centralized as opposed to the traditional one, more specific and distributed. Okay. Some of you actually might like the distributed one better, but some of you might like the central one better. Okay. Hey, don't be surprised that Polly might ask in a pop-up quiz. Do you prefer the distributed routing or the centralized routing better? Okay, somewhere this week or next week. All right, so let's go on and dig into the first topic, routing algorithms. Okay, and you see that a network on the internet is composed by a bunch of routers and hosts, and there are links connecting these routers and hosts. And we are passing data from one node to another node. And you know what? If you think of all these nodes as vertices and the links connecting the nodes as edges, vertices and edges connecting the vertices form a what? A graph. And therefore, you can actually utilize some of the graph algorithms you've learned in the algorithm course. And finding a route from one node to another on the internet is essentially trying to find a path from one vertex to another vertex on a graph. So first video here explaining routing algorithm is to introduce what is a graph, and you see that a network is a graph.
Now the core of chapter 5, the routing algorithms, or the routing protocols. So a good routing protocol there should be able to identify good paths or good routes from the sending host to the receiving host through this network of interconnected routers in the middle. So that is essentially trying to come up with a path. Okay? A path is a sequence of routers, one connected to another, and connecting the initial source to the final destination, okay? Such that this path here is the least in cost, so we pay the least. Or the delay is the shortest. Or the promised bandwidth there is the highest, therefore the congestion level will be the lowest. Okay? So finding a good path, that is the goal of a good routing protocol or routing algorithm. It's also one of the top 10 problems in computer network, just like reliable data transfer, just like congestion control. In the next couple slides, Polly is going to introduce this new term called graph. A network, okay, of routers interconnected by links is a graph. So let's focus on the network in the middle here. What you see is that we have router U, router V, W, X, Y, Z. So we have a set of routers, okay, and there are 6 of them. Now, between the routers, we have also links. So link UV here connects router U and router V. Similarly, UX here connects router U and router X. VX, V here, X here. Yeah, VX is the link connecting router V and router X. Link VW, connecting router V and router W. So you see, we can go over all the links defined here, and this forms the set of links interconnecting the routers. And coincidentally, a graph is also defined in a very, very similar way. A graph consists of the set of nodes and the set of edges interconnecting the nodes. So N here stands for nodes, and here, E here stands for edge. So if you consider the routers being nodes, yeah, so the set of router here is the N here. If you consider links being the edges, then E here is the set of the edges. With the set of nodes, set of edges interconnecting the nodes, we do have a graph. So a network here is also a graph. And such an abstraction is really, really convenient later on when we're introducing the algorithm. It could also be useful when we're talking about other kinds of networks. So for example, in the application layer, chapter 2, for P2P, okay, you see there, okay, there are peers here, there, all around the internet. And we establish connections between the peers, right? So we could do what? P2P communication. So if you consider each of these peers as a node, and these TCP connections or UDP connections connecting the peers as an edge, there, you also have a graph. You also have a P2P network. And you can also run a routing algorithm, okay, on a P2P network, if you think about it. And now we can talk about this other thing, okay, it's called the link cost. So associated with each link, okay, on a graph like this, you see a number nearby, that is the link cost. To denote the cost of a link connecting router X to X prime, we use this notation, CX prime. So CWZ, connecting router W to router Z, a link here, yeah, the cost of that link is 5. Right? That cost, okay, can be set in a variety of ways. For example, set it as the inverse of the bandwidth available. You can also set it to the inverse of the traffic level. You could also set it simply to a constant, such as, 1. Every link costs the same, 1. Okay. So that is link cost. Now the cost of a pass, okay, is essentially also very simple. From the source x1 to the destination xp, it's the sum, okay, of all the link costs connecting from the source to each of the routers along the path, all the way till the destination. So it's the sum of the costs from the source to the first hub router, x2, c, x1, x2, plus c, the first router to the second router, x2, x3, and so on and so forth until the last router, xp minus 1, to the final destination. Okay. So let me use an example. Let's say traversing from U to Z, and we take this path. Yeah. The cost of the path will then be adding 2 to 3 to 5, and that will be 10 here. All right. So the goal of routing algorithm is essentially to find the least cost path, okay, between a pair of nodes, okay, from source to destination.
So you see, routing, the goal is to find the shortest least cost path, okay, in a graph. All right, so the second video here introduces the 2 routing algorithms that we'll talk a lot more about next. And again, similar to the graph introduction video, you see CXX prime, that's a notation to represent the cost between node X and X prime. So in this video, in the second part, you will see Polly introducing notations as well. Okay.
And Polly will be introducing 2 routing algorithms next. First is called the link state algorithm. Second, distance vector. The link state routing works this way. Inside the network, each router, okay, in the router, it implements an algorithm. Before this algorithm can be triggered, the router needs to wait to have the complete topology and link cost information. What I meant by complete topology is this. Each router will need to know N, the set of routers composing the network. E, the set of links interconnecting all these routers in the network. And link costs of all the links, okay, connecting the routers in the network. So each router needs to know how the network looks like globally before the routing algorithm can be triggered. Another characteristic is this. The link state routing algorithm will run in just one pass. So provided global information of the network, trigger routing, route computes, and completes. As a result, each router not only knows the best route to all possible destinations, it actually knows, okay, all the best routes from arbitrary source in the network to arbitrary destination in the network. So the router there, very informative, knows how the network is like entirely and knows all the paths, okay, for all the possible destinations and source pairs. On the contrary, in distance vector, routers no longer require global information. The routers also do not do one-pass route computation. Rather, the router only needs local information, namely, a router only needs to know how it's physically connected to the immediate neighboring routers and the link cost to the neighboring routers. And that's all. The route computation begins. With very minimum information, the computation gives you suboptimum results. Okay, so each router there, after running the distance vector algorithm, will know just slightly better than, nothing. And that information is definitely not quite good enough to give us the least cost path. So what distance vector routing does is there. Each router will then, after some initial computation, exchange the result of the computation to the neighboring routers. Neighboring routers would also exchange what they know slightly better to the router here. Now, this router in the middle, after receiving slightly better information from the neighboring routers, can recompute and see if even better paths have been discovered. Okay, so if the router again discover, better paths, then tell the good news to the neighbors. Similarly, neighbors would also tell slightly more information to the router. Okay, as such exchange expand, gradually traveling through the network. Okay, all the routers in the end learn about converge to the least cost path. Okay, so the process you see, computation, exchange, computation again, exchange again, computation yet again, exchange yet again. So the process is very iterative. It's going to take some time, but eventually, as the information propagates through the network, everyone converges to the least cost path. So a very different model of doing route computation. Link state routing being global, distance vector routing being local. Now, another way of classifying the routing algorithms is this. By judging at how the routes are being updated. Static routing is not updating the routes. So this is only for the network that is not changing frequently. And we know that this kind of network doesn't really exist these days. So all the routing algorithms that we're introducing are working this way, dynamic. That is also saying that routes can change, link costs can change. Routers could suddenly be dead and then or suddenly being booted up. So we'll try to update these routes, repeat the computation, periodically, or in case we detect there's a link cost change or no change, or some other changes.
All right, so I'm sorry, the notations are actually in the next video, so it's coming up. Here, guys, we have a pop-up poll today, so it's not a quiz, So what I'm asking here on the live channel is based on the very limited knowledge you've learned about the two routing mechanisms, one called link state, the other called, I said list state, so I meant link state, and the distance vector routing. So one is based on global information calculation. The other is calculation based on only local information. Which one you like better? All right, so it's just based on your intuition and based on the very limited knowledge that you know of. There's no need to tell why. So that's pop-up poll number 1. Okay, good. And next, let's start introducing the first routing algorithm. It's called link state. All right, and in this video, then you see Polly telling the general idea of link state routing, and then of course the notations that you need to know before Polly introduces the pseudocode of link state routing algorithm.
Now finally, the link state routing algorithm. So what's implemented there essentially is the Dijkstra's shortest path algorithm. This is very well known in graph theory. Again, as mentioned, in order for this algorithm to work, we need the global information, network topology, link cost. And this information is acquired by sending these link state broadcast messages. So each router will be sending information about itself and how it connects to other neighboring routers and what is the link cost to the neighboring routers. And that information from each router needs to be broadcast around the entire network until every router on the network receives link state broadcast report from every other router. Then all nodes will converge to the same information, same network topology, link cost, and therefore beginning to compute the least cost path. So once the computation is done, we get the forwarding table to install to the data plane. Now, something extra is this. The computation itself is iterative, but it's not working iterative like the distance vector. The distance vector's iteration is computation, exchange, and computation, exchange. The computation part and the exchange part is being iterative to each other. The iterative here meant, okay, there's a loop. Okay, the computation is actually working a loop, iterating through multiple loops. Therefore, okay, if we have k destinations, it takes 8 loops or 8 iterations to complete the route. Okay, so yeah, the algorithm itself is looping within itself, but the computation will be done, okay, all at once without exchanging further information with the neighboring routers. Let me introduce these notations before I bring up the pseudocode for the Dijkstra algorithm. First is CAB. This is the cost of the link connecting router A and B. You should know already. Yeah. What's a little bit surprising to you is this. The cost, CAB, could be infinite, okay, because there's no direct link connecting the two routers, and therefore the cost is infinite. Second notation is this, DD. Okay, small d here is indicating that for a particular destination, the path from this router doing the computation to this destination, what is the cost of the path currently? Okay. So capital D here actually stands for distance. This is also saying what is the current distance to a particular destination D for this router doing the computation. Now, PD here, D again is the destination, okay, and PD is to indicate for this router to reach the destination D, okay, along all the routers on the path. What is the previous router before reaching D? Okay, so predecessor node along the path until reaching D. And prime is the set of nodes whose least cost is already known.
All right, so with that notation in mind, C is the link cost. Big D is the path cost. Okay, so make sure you know the distinction. Let's start talking about the pseudocode of link state routing algorithm. And it is actually called officially Dijkstra algorithm. If you have taken the algorithm course before, you might have heard of the term Dijkstra routing. All right, and in this video, it's a little bit long, almost 6 minutes, but you see that you can tell from the pseudocode there are essentially 2 parts. First is the initialization part, and then the iteration part. There's a loop there that goes iteratively, as you heard in the overview video that it's iterative. Link state routing is iterative.
So here's the pseudocode of the Dijkstra algorithm. There are 2 phases, the initialization phase and the looping phase. A looping phase looks really complicated, so let's not worry about that part yet, and focus on the easier part, the initialization phase. So what we're doing first is to initialize the n prime, the set of nodes we know already the best route to. And we are quickly including A. The reason is this. Whenever we execute once the Dijkstra algorithm, we give also the source of the path. So A here is the source of the path we're trying to discover. In fact, after running through a Dijkstra algorithm, we will discover, okay, the shortest path to every other node in the network. Okay. Now the source, in case A is also its destination, hey, it's trivial, isn't it? We just don't send it down. Send it to 127.0.0.1, the IP address for the local host. So we can initialize n prime to just the source node safely. Second thing we do is actually a for loop here. Okay, inside the for loop, we'll go through all the nodes, okay, in the network other than the source. So all other nodes, okay, and for each node, okay, B, we check whether it's directly connected to the source. If it does, we've discovered a way to go to this particular destination, isn't it? And the distance to it is the link cost between node A and node B. Now, if the node is not adjacent to A, then it's going to trigger this line here. No route has been discovered yet to this destination B. Therefore, distance to the destination, infinite. Okay. Now, from the description, you probably also see, in order to find all pair shortest path, you need to repeat the Dijkstra algorithm, providing a different source address. Okay. Now the exciting part, the looping phase. It looks a bit complicated, but if you focus first here, okay, the loop is going to go until all the nodes are in the n prime set. That is also saying that the loop is going to go until all the shortest paths have been discovered. Okay, the shortest paths to all the nodes have been discovered. And you probably guess that, hey, one of the things that will be changing in the loop is the n prime set. Okay. Yeah, indeed. Okay, the first part in the loop is exactly to do that. We are gradually adding nodes into the n prime set. Okay? And the node we pick to add is this. Okay? The node such that the distance to it is currently the minimum. Because adding this I to n prime set is also saying that the best route to I is already discovered. Okay? So why is the minimum di here is suggesting that the best route, this is also the shortest distance to I. Now, think. Originally, okay, we have A in the n prime set. Okay, the D, B there existing with significant values are these. The nodes directly connected to the source. And therefore, the distance to each of these nodes, okay, is the link cost. Now, in the loop, okay, the first two lines here is going to include what? The node with the smallest link cost to the source into the n prime set. Is that making sense? Okay, is the shortest distance, okay, to that particular node exactly that? Is there a way to discover another path to that node that is going to be lower than the link cost between A and I? Not possible, right? Because all the other links cost is higher. If there exists another path to I, the cost is definitely going to be longer than this because all the other link costs are higher already. Okay? So di here is indeed the minimum, and I here we've already discovered the shortest path. So it's safe to include it into n prime, in fact. Now, having added I to the n prime set, this is also saying that we already discovered the shortest path to I, and the shortest distance is di. So I know there is something really nice to exploit. Okay? Through I, we can potentially discover shorter paths to other nodes. Okay? We have not yet discovered the shortest path. Okay? So what we're doing here next is to go over for all j nodes that are directly connected to I. So for all the neighbors of I, and not yet in n prime. So all the neighbors of I that we have not yet discovered the shortest path, then we update dj. Okay, and that is what this formula is saying. Okay. So the new dj is the minimum of the two, the existing dj and okay, the distance to go okay, from j directly to I and di. So the shortest distance from I to the source. So di plus Cij. So this is what the comment is saying. The new cost to j is either the all cost to j or the shortest path to I plus the link cost from I to j. So what we're doing there is to update dj. Okay, if there is a shorter path, that's just editing. If there's a shorter path, that's override the bad path. Okay, things like that. So you see, what we're doing in the looping phase is actually not much different from what we're doing in the initialization phase. So this part of the looping actually corresponds to this part of the initialization, isn't it? Okay, including nodes that we know for sure. Okay, what is the shortest path? And then here actually corresponds to this. Okay, try to discover the shortest path possible. Okay, by updating based on the information that is known.
All right. I hope that's straightforward enough explaining the pseudocode link state routing. If it's not straightforward enough, don't worry. Let's go over an example that usually helps. And the example is a network, real network. But to go through the entire algorithm takes a while. So I break it into two parts. Okay, so let me play the first part, which is to go through the initialization phase and the first iteration of the looping phase. And you'll see Polly trying to fill a derivation table there to tell which is the next node to include to n prime.
So that was the walkthrough of the pseudocode. I know it might appear a bit fuzzy to you. Let's go over a concrete example. Right. So in the example, again, we have 6 routers and their links. Each link comes with a cost. And let's assume U is the source, and Dijkstra is going to do the computation starting from U. Now, the initialization phase says let's include the source into the n prime. Therefore, we see U here appearing in n prime. Next thing is to go over all other nodes. Okay. So X, W, V, Y, Z. Those who are adjacent to U, then we set the minimum distance to it, set the predecessor to reach it. Otherwise, if they're not directly adjacent to u, set the distance to infinite. So for y and z, we'll see. Okay, this should be infinite. And for VWX, V, the distance to V should be what? The link cost between the source and V. So between U, V, link cost 7. So 7 should appear here. The predecessor for such a pass definitely going to be A, because we just added A to the n prime set, right? And we're reaching V through a direct link. Therefore, the previous node must be the source, U. For W, link cost being 3, so 3 here, predecessor again U. For X, link cost being 5 and predecessor U. And yeah, 7U, 3U, 5U, infinite, infinite. Okay, so we just finished initialization phase of the Dijkstra algorithm on the example. Now, entering the looping phase. First thing we do in the looping phase is what? To find the I that is not yet in n prime such that the shortest distance to I is the minimum, and we add that I to n prime. Alright, so let's go over the di. Okay. 7, 3, 5, infinite, infinite. Which one is the minimum? Yeah, 3 here is the minimum. Therefore, I is w this time, and we'll include I into the n prime set. That is why. Next, we see u and w both in the n prime set. And then we can now do the second thing we do in the loop. We'll update the minimum cost. And we're going to do this for all the nodes adjacent to, what is the I being added there? W, right? So we'll go over all the nodes adjacent to W. Okay, and that is now already in n prime. So who are the nodes adjacent to W? X, Y, V, oh wait, oh yeah, Y disconnected, okay, because there's one link here, and U, all right. But you know what? U is already in the n prime set, so let's remove this. So there's just 3 nodes, okay, can potentially be J, and we need to update the minimum distance and the predecessor node. So what we'll be doing here is to exploit W here, okay, as a hopping node. So V here, okay, there's another pass, right? Originally, we had this direct link, but now there's an alternative pass through W, which is what? 3 plus 3, okay? The minimum distance to W plus the link cost between V and W. And that is how much? 6. Is 6 better than the existing minimum distance to W? Existing minimum distance to W, existing minimum distance to V is 7, and that is indeed better. Okay, so 6. And in case it's better, the new pass is better, we'll set the predecessor to the new node we're hopping through. So V is now taking W as the predecessor, and the cost, minimum cost from the source, is only 6. Second neighbor, Y. Previously, dy infinite. Currently, if we use W as a hopping node, 3 plus the link cost between W, Y, 8, together 11. Obviously better than infinite, and the predecessor is what? W. Third neighbor of W, X. Exploiting W as the platform, hopping, and then adding the link cost between X and W, that is 7. Is 7 better than dx? Dx was 5, 7. Oh, yeah, in X's case, not better, so we'll keep 5 here. Z not being connected, it will remain the same, so remaining infinite. And therefore, we should see 6W here, 5U here, 11W here, and infinite here.
All right, first iteration of the looping phase. So far, so good. Let's play the second part and derive the full derivation table.
So what do we do next? Well, we're in the loop, and we are not in the condition to end the loop yet, so we're not yet done. We have only U and W in n prime. Okay, there are more nodes, okay, we could consider adding to the n prime set. And the way we add to the n prime set is to pick I such that the I is the minimum. So dv6, dx5, dy11, dz infinity, which one is the minimum? Yeah, x is the one we're picking this time. So we'll include x into the n prime set. And we see there, x here is the I, So we'll be examining all the nodes adjacent to X next. So X is here. The adjacent nodes include U, W, Y, and Z. But you see, yeah, we'll be going over all the nodes adjacent to Y, but not yet in M prime. U and W are already in M prime, so we will not be updating DU, not updating DW. So let's update DY. The way to do it is to follow the formula. What is dy now? The current cost, 11. What is the newly discovered path cost? What is the new path? Well, one can actually go to X and then using X as a hopping platform to reach Y. And the total cost is 5 plus 7. That is 12. This time, the new path is actually not better than the existing path. So we keep 11W here. The other neighbor, Z. Okay, what is the current cost? Infinite. So infinite here. Cost to X is 5. And the link cost from X to Z, 9. So the new path discovered is 14. And the predecessor is X, which is better than infinite. So 14, X here. Now, V is not even a neighbor of X, so we'll just not update VV and PV at all. So, and that's why we see 6W here, 11W here, and 14X here. So this is the second iteration in the loop. And next, pick I again with the minimum DI. 6, 11, 14. Therefore, we include this time V into the M prime set. Right? So 6 here included, V included to the M prime set. And therefore, the I is V. So I here. We'll go over all the adjacent nodes of V, which includes U, W, and Y. And that's now already in M prime, so that includes U and W. The only node that we need to actually update the D for is Y. So we'll be updating DY. Existing DY, 11, right here. So if V here is the hopping platform, the cost to go to V, the cost to go to V is actually what? 6, okay, through W. The link cost from V to Y is what? 4. So 6 plus 4, 10. Is 10 better than 11? Yes, it is. So let's update it. And this time the predecessor is what? V. Okay, so that is also saying this path here was no longer good, and this is actually a shorter path. Now Z is not directly adjacent to V, so we just leave this entry down. That is why we see 10V and 11X. Good, so yet another loop. We pick another I with the minimum DI. 10, 14, therefore we pick Y next. And Y is included into the M prime set. So Y is our I this time. So Y here. Go through all the adjacent nodes that are not already in M prime. So X already in M prime, W already in M prime, V already in M prime. The only one that is not in M prime is Z. So let's try to update the distance to Z. And again, follow the formula. Existing distance to Z is 14, so 14 here. Using Y as a hopping platform, which says, the minimum distance is 10, and the predecessor is V, so it's this path here. And we are adding the link cost from Y to Z, which is 2. 10 plus 2, 12. Oh wow, so this new path here is better than the existing path, so let's update this to 12, and the predecessor is what? Y this time. And so we should see, 12 and Y here. And the last loop is to include the only remaining node, that is Y, actually, that is Z here, okay, into the M prime set. And there are no neighbors adjacent to Z that's not yet in M prime. So this part we don't have to execute for the last iteration. Okay. And by now we've completed the Dijkstra's shortest path algorithm, okay, for an example of 6 nodes.
All right, so sorry that I just discovered that many of you, in fact, all of you have heard about the Dijkstra algorithm. So the video, the pseudocode will be trivial for you guys, and good for you. And
you guys then know Dijkstra is the algorithm to build what? The shortest path tree. And shortest path tree with the root at the nodes we started included into the n prime, right? Good. And so the last video of the example is essentially, yeah, all of you have heard about Dijkstra. So last video, again, trivial, is to see how we convert the shortest tree information to the forwarding table such that the router will insert into the data plane, and therefore when packet comes, matches the destination address, quickly forward to the right outgoing interface, right outgoing link. Okay, and hey, after this video, we'll exercise link state routing with quiz 40.
Just a couple more notes to construct the shortest path to a particular destination from the source. Say from U to Z. Okay, what it needs to do is just to track the predecessor node. Okay, and let's trace it all the way back to the source. So Z is the destination. That's traced back from the predecessor of Z, which is indicated here being Y. And who's the predecessor of Y? Yeah, it's stated here, which is V. Who's the predecessor of V? Stated here, W. Who's the predecessor of W? U. That is the source. Yeah, therefore, you see, this is the shortest path from U to Z. The shortest path to X, yeah, indicated by the predecessor, which is U itself. Okay. And so we could actually reconstruct the shortest path by just tracing back the predecessors. Okay. And you see also here, if we trace back, okay, for all possible destinations to the source, you see also a tree rooted from the source U, okay, to all the destinations. And this is indicating also the shortest path to all the destinations. And such a tree is also called the shortest path tree. And Dijkstra algorithm there is also used to calculate, okay, to generate such a shortest path tree. Second note, the D values, okay, when we're picking the I, can have a tie. So in that case, we just have to break the tie and picking one of those.
All right, that takes us to quiz 40. And it's better that I, go to the whiteboard mode. So this is quiz 40. Okay, good. And hey, we also have a network, and this one is obviously different from the network in the video. So I ask you in the first part to fill the derivation table, particularly step 0, which is to go through the initialization part of the pseudocode. All right? And then, second part of quiz 4 is then to fill step 1. Okay, that's the second row here. Okay, and that is to go through the looping phase for one iteration. Okay, just one iteration. All right? And it's now time to go to the score space, channel W13 and quiz 40. Okay, good. And guys, I think that some of you might be just writing, deriving on your notebook or some sort of pad. Either way, if you are using a pad, take a screenshot of your derivation. If you are writing on a notebook, just take a photo of the notebook and upload it on the score, the channel W13 quiz 40. That will save you some time typing up the exact letters for each row. Okay, so if you want to type up, that's also okay. Okay, good. And how much time do we need here? Given that all of you know Dijkstra algorithms, then maybe just 4 minutes? How about that? Let's go ahead and start counting time. 4 minutes, guys.
Okay, so you see it takes time for Polly to derive the table as well. Okay, so hey, I see Yunru, good to see you, replying early. I think the first row, very close, except that you still need to tell what the predecessors are. So DV is 2, but PV, I suppose for first row, for step 0, it's always U, the first node. But you see that for the second row, it's not that obvious. You do need to write them out. And if I read the second row, which is step 1, Yunru, hey, my answer and your answer is a mismatch. I think it's for Y, no Y. Yeah, the shortest distance to Y is not quite 1. Let me see if other students... Okay, but very good to see you answering first, Yunru. Let's see if the other what the other students said. Okay, so I guess many teams have tried to correct the answers. Yeah, because it's a little bit tricky. Sometimes if you just, mistaken one number from another, because it's a graph, right? Sometimes you need to trace things. It's not that easy. So I think Anthony here, team 9. All right, looks the same to mine. I have 2U, 4X, of course 1U, and 2X for the second row for step 1. Very good. And I think, well, at least Anthony's and mine agree on each other. Chances high that team 9 is correct. Let's see, team 1. Oh, team 1 is really nice, right? Because among the 3 nodes adjacent to U, V, W, and X, which one has the shortest distance? X. Therefore, X is selected to be inserted into the n prime set. That is very clear as indicated by Sam's table. And then step 1, 2U, 4X, okay, that's a 4, okay, and 2X, sorry, the resolution is not very high for me. And guys, What will be the node we select to include in n prime for step 2? It's a little bit tricky now, right? V and Y both have shortest distance. Which one do you pick? In such a case, usually there's a tiebreaker. For example, if it appears in the exam, Polly would then say, hey, let's use, that's tie break. The nodes having the same shortest distance to n prime by the alphabetic order. If that's the case, then we'll pick V, right? Because V is alphabetically ahead of Y. All right, good. So same, perfect. And carries a little bit more information, showing the table this way. And let's see, Sherman. Okay, nice. Just take the screenshot and then work on it. So UX 5U 2U 5U 1U, very good. 2U 4X and 2X, very good. Sharon, you are also perfect. Let's see, Gao Pu, Team 19. Oh, nice. Yeah, this is a set, and this is a set. Wow, you have mastered how to present a table in Discord. This is nice. Hey, you might want to teach us how you do this. Okay, so let me see the actual code. No, I actually don't see it. I just, okay, very interesting. Gao Pu, how did you do this? Really nice. Okay, in case you find time, Gao Pu, tell us how you do this, typing up a table on Discord. It's a markdown. Okay. Can we see the source code? All right. Nice. Really nice. Thank you for sharing. Yeah, lots of that kind of mark. I see. Very good. Team 6 is also correct. Team 2, let's see. Using the straight line to delimitate. Yeah, I know. Yeah, 3. I don't know how you call that mark. Yeah. Got it. Thank you. Yunru modified. Very good. Okay, then you get your special mark here. All right. Team 10, also perfect. 15. Oh, thank you for telling the process. Very good. And showing the derivation table. Wow, thanks. And Kelvin? All right, perfect. Okay, guys, if you manage to complete quiz 14 here online, you guys should not have problem working on the final exam, the last exam. All right, good. Okay, and you know what? It's time to take a break. Okay, it's now 11:20, which is the time we are supposed to resume the lecture, but let's take a break. But let's take a shorter break. How about resuming the lecture at 11:25? All right, so let's take a break. let's come back and resume the lecture. Okay, good. And hey, link state routing is essentially Dijkstra algorithm. And there are some known issues about link state routing. First is the computation cost. It's n squared.
Now with the two examples walked through, you see the Dijkstra's algorithm, although look a bit cryptic at the beginning, it's in fact quite straightforward. Initialization phase, 2 steps. Looping phase, 2 steps. Looping phase is the one that we take multiple iterations, we spend more time with. So that is going to bound the complexity of the Dijkstra algorithm. And within the looping phase in each iteration, which of the steps is taking the most time? Yeah, the second step. Inside the second step, we're actually checking all nodes j, okay, that is adjacent to the node we just added into n prime. Okay. And inside each iteration in the inner for loop, what we do is this, the min operation. And this is in fact to compare the value of the current shortest path to the newly discovered path, right? So d to I plus the link cost between ij. So it's a comparison between this value and this value. So you have the looping phase, and inside there's an inner loop that is doing a lot of these value comparisons. Now, if we consider a fully connected network, that is the worst case for Dijkstra algorithm. Inside the network, there are n nodes. Okay. In the first iteration, so only the source is in the n prime. How many j's is connected to the source? Yeah, it's fully connected. Therefore, n minus 1 nodes, they will all be j, and we'll need to do min for each of these j. First iteration, we'll need to do n minus 1 comparison. Second iteration, how many? Because there's one more node being included into n prime, so number of j in the second iteration, only n minus 2. Third iteration, and we can go on until the second last iteration, we have only one node remaining connecting to the new node being added to the n prime. In the last iteration, the second step is not going to be called because there's no j remaining. So if we add all these together, this is the number of comparisons. N multiplying n minus 1 divided by 2. And this is in the scale of n squared, big O n squared. So big O here is actually to say that the Dijkstra algorithm in the worst case runs in the scale of n squared. That means the time complexity, the growing trend of Dijkstra algorithm is this. When n approach where the network goes really big, the time requirement goes in this trend, like an n squared curve. Now, if it's only big O n, the curve is linear, a straight line, sorry, the line is not very straight here. Now, there's an implementation available for Dijkstra algorithm such that we could do away with only n log n. Now, this is better than n squared. Right? So again, n is here, n squared growing really fast here, and n log n is actually kind of in between. Faster than the pseudocode we've investigated, and better than a linear algorithm. So, nice to have an efficient implementation, even though the original Dijkstra algorithm is not so good.
Yeah. So the time complexity issue, big O n squared, can be reduced to n log n. Now, the second issue is called oscillation, and this happens when the network mean sets the link cost to the traffic load currently on the link. You see, Polly explains how that oscillation happens.
There's one very special issue with link state routing that's called the path oscillation problem. And it happens when we set the link cost dynamically based on the amount of traffic going on the link at the time. Now let me explain using an example. So we have 4 nodes in the example, A, B, C, and D. A is the traffic sink. All traffic goes to A. B, C, D are traffic sources. A generates one portion of the traffic and send it over past BA. E generates E portion of the traffic. E here is a very small amount, much smaller than 1. And C is taking the CBA path to send traffic to A. D generates also one portion of the traffic and it's taking path DA to send to destination A. And at this point, we need to update the link cost based on the traffic going on the link. So for link DA, amount of traffic is one portion. For link BA, amount of traffic is what? One portion plus the E portion from C. So total cost, 1 plus E. The cost for link CB, amount of E traffic from C only. You see also here, okay, this direction, BC, there's no traffic, therefore link cost is 0. Similarly for AB, similarly for AD, and similarly here for both direction in link CD. So we finish updating the link cost. After a while, link state routing is going to trigger Dijkstra algorithm running again, right? As I described, link state routing is a dynamic routing algorithm. We do periodic update, and sometimes we use also network events to trigger recomputation of the routes. Link state routing there does periodic recomputation. Okay? It's going to recompute the routes based on the link cost now. So let's see. B here, we'll see two possible paths to go to A, right? One is to go counterclockwise to A, the other clockwise to A. So this direction here, the cost is what? 1 plus E, because there's only one link and the link cost is 1 plus E. If we take this other path, B, C, D, A, yeah, the path cost is the sum of the link costs, 0 plus 0 plus 1. Okay, so if we take the clockwise path, okay, to go from B to A, cost is only 1. And this is 1 plus E, therefore B is going to choose to go this way to send traffic to A. C, also see two possible paths. Okay, if we take this direction, cost is E plus 1 plus E, and that is 1 plus 2E. The other direction, cost is 0 plus 1, therefore 1. And therefore, C would choose to go also clockwise to send traffic to A. Similarly, D sees also two paths. Okay, this direction here, cost is 1. This direction, 0 plus E plus 2 plus E, 1 plus E. So altogether, 1 plus 2E. So still, okay, this direction better. So D is also going to take the clockwise path, okay, the same path to A. So after the route computation complete, you see B, C, D all change to send traffic clockwise. And then we need to update the link cost again, right? So given the previous cost, we come up with the new routes, and we will then, okay, update the link cost, and we come to the new cost again. What is the new cost now? Okay, on link BC, yeah, there's only one portion of the traffic. On link CD, yeah, 1 plus E. On link DA, 2 plus E. And that is why we see 1 plus E, 2 plus E, and all the rest of the links, 0. Once we update the link cost, after the next period that the Dijkstra algorithm is triggered, we compute new routes. So B will then try to see the cost to go this direction and the cost to go the other direction. The cost going counterclockwise is now 0. Cost going clockwise is now 1 plus 1 plus E plus 2 plus E. That's 4 plus 2E. So dominantly, BA is the better path. C's cost going this direction, 0 plus 0, cost is 0. The cost of the other direction, 1 plus E, 2 plus E, 3 plus 2E. So C is going to switch going this direction to send the traffic. What about D? Going this direction, 0 plus 0 plus 0. Going this direction, 2 plus E. So D is going to switch for the first time to go counterclockwise. And that's why in the next moment, you see traffic begin to change direction completely. Okay? From all clockwise, okay, one period before, to counterclockwise the next period. So given these new costs, we calculate the new routes all going counterclockwise, and we update the new costs again based on the traffic. DC is now 1. CB is now 1 plus E. And BA now 2 plus E. And that is what you see here. 1 plus E, and 2 plus E. As a result, B sees this pass costs 0. This pass costs 2 plus E. B switch the other direction. C sees this pass, really high, 3 plus 2E. And this other direction, 0. D, this direction, 0. This direction, super bad, 4 plus 2E. So all of them would switch back like this. And the link cost gets updated again. 1 on this link, 1 plus E on this link, and 2 plus E on this link, which is identical to 2 periods before. Okay? And you see the next period is going to be like, yeah, the previous period. And the traffic is going to oscillate infinitely, right? Clockwise, counterclockwise, clockwise, counterclockwise. So that is the path oscillation problem if we set link cost dynamically in link state routing. Okay, that's running the very straightforward Dijkstra algorithm. Just be careful here.
Yeah, so that is the oscillation issue. Therefore, these days, the network admins are careful setting the metrics to estimate the link cost. Using the traffic load, that is too dynamic, and you end up having route oscillations like that. Good? And the third issue is this. Hey, when we are introducing the Dijkstra algorithm, or even in the quiz 40, you are given a topology, you are given a network so that you can start doing the Dijkstra algorithm. But the routers, when you start it up, there's no network topology inside. So even though you coded the Dijkstra algorithm in, there's nothing to compute about. Yeah. So in link state, there's an issue. That is for each router to collect the information, collect the entire network topology. And that is done in link state routing using the link state broadcasts.
To put simply, link state routing works this way. Each router implements the routing algorithm. It's going to wait until the total information of the network is in place. Then it calls the Dijkstra algorithm. At the end of the calculation, we get the least cost path from this router to every destination possible in the world. So that is essentially the shortest path tree. Now that router being the root of the shortest path tree, we'll see there are multiple branches out to the rest of the world. Taking one branch, it gives you the shortest path to a certain set of destinations, another branch to another set of destinations, yet another branch to yet another set of destinations, and so on. From the tree structure, okay, we can construct the forwarding table, and that is how the forwarding table is calculated in the control plane. Next is just to install it into the data plane. Now, the only part I'm going really quick without mentioning much is this: how we get the total network information so we could apply the Dijkstra algorithm in the first place. That is done through this link state broadcast. Each node, okay, in the network is going to generate link state report based on very local information. That includes the ID of the node itself, the ID of the immediate neighbors, and the cost, okay, on the link to these immediate neighbors. Okay, so these are the local information. Node, the neighboring nodes, and the link cost to the neighboring nodes. So all these local information is going to be in the link state report coming from the node. This link state report is going to be broadcasted, meaning, okay, going out through the entire network, being received by all other nodes. So all nodes eventually will receive link state reports from every other node. Okay. And these link state reports from every other nodes, including the node's local information, is going to be used to restore, okay, the total network. Let me give you an example to illustrate how that is done. We have a very simple network here, only 4 nodes. Okay, you see, U connects to V, U connects to W, U connects to X. Okay? So if we are node U, okay, and generating node U's link state report, it's going to contain this: the ID of the node itself. Yeah, there are 3 neighboring nodes, V, W, X, and the cost on the link to these nodes, 5, 3, 7. So U to V, link cost 5. U to W, link cost 3. U to X, link cost 7. Similarly, V is going to generate its link state report, which is going to contain only 1 entry. It connects to U, link cost 5. The link state report from W should look like this: 2 neighbors, U and X, cost being 3 and 2. Link state report from X is contained 2 entries, U and W, link cost 7 and 2. So each of these nodes, U, V, W, X, is going to broadcast your link state report. And every node in the network is going to receive its own local information and every other node's link state report. Therefore, node U here is going to receive the link state reports from V, W, and X, which we know already look like this. The way to restore the network topology is this. Okay. Node U knows the local information. It connects to V. It connects to W. It connects to X. Cost is 5, 3, 7. Now, seeing node V's link state report knows that V and U is connected. Cost is 5. V, U, I'm U, so I know. Okay, and the cost is 5. W's report is going to tell, okay, the cost to U is 3, which you already know. Oh, W is also connected to X with link cost 2. So W connect to X link cost 2. X report says I connect to U, so X connect to U, you already know. X reports also that it's connecting to W link cost 2, which you already have. And you now manage to reconstruct the total network information from receiving link state reports from all the nodes in the network. And it's contributing also so that other nodes receiving U's link state reports can also reconstruct the total network. So you see this one here, U connecting to VWX. Yeah, isomorphic, okay, of the network there.
Yeah, so that problem, getting the total network information, is addressed by the link state report floods, okay, from each of the nodes, right? But those who are keen about designing protocols, you might be sensitive to know that, hey, if the network grows bigger, then these link state floods will be all over the network and there'll be more traffic. You're right. In fact, in each router, you need to maintain that network information. A bigger network requires more memory space as well. Yeah, that's the most serious issues with link state routing. Scalability issue. When N grows, memory space, traffic overhead, and computation overhead we have already talked about in issue 1 will also grow higher.
So that was the last piece of the puzzle, link state routing. Other problems you see here. Now you know a little bit about the link state broadcast. Yeah, some of you might see this. These link state broadcasts, it's going to travel the entire network. And it's coming from every router. So you have n copies of these packets going to n nodes. The bandwidth consumption is again at this scale. And to store the topology information in the router, right? So we discussed the complexity of Dijkstra algorithm. We only talk about the time complexity. We have not yet talked about the space complexity. It's also huge, right? In the worst case, you have n nodes fully connected to every other node. Then you have what? N square number of links. I need to store costs, okay, for all these links. Ugh. Not very scalable when the network goes big, when N goes large.
Yeah, so scalability issue, serious in link state routing. Therefore, distance vector, the distributed one, the one based only on local information to do routing, to discover the shortest path route, okay? And in this video, you will see the motivation of distance vector routing and the basic idea of distance vector routing.
So you see, link state routing works fairly well for small networks where N is small. For access network, institutional network, local area network, it might be okay. But for the entire internet backbone, there's no way we use link state routing. And that takes us to the second routing algorithm, okay, distance vector in the chapter. So distance vector routing is exactly here to address the space complexity, to address message exchange complexity in link state routing. If you think about it, the reason that the link state routing takes so much space, requires sending of so many messages, is because in order for Dijkstra algorithm to run, we need the total network information. So the question to ask is this: can we come up with a path? Can we discover best paths, best routes without knowing the global information? You know what? It's possible. We just need to be a bit patient though. Okay? So Polly here might have two neighbors, Alice and Bob. Bob and Alice do not know each other. Okay? There's no path existing from Bob to Alice. But if Polly shares how Polly knows Alice to Bob, then Bob will know that there's one way, right, to reach Alice, which is through Polly. Okay? So I tell my neighbors, and you tell yours, okay, about what you know. Gradually, okay, the network, okay, will spread the good news out and discovering a path, a route, okay, to every other node in the network. That is the general idea of distance vector.
Yeah, and to show that will work, or to give you the basic spirit of distance vector, let's walk through quiz 41 to 43 here. Okay, so here's the first one, 41. So pick the next router here is the problem you need to work on, and this is part 1, so there's part 2 and part 3. All right, so guys, you need to pretend that you are router X. Okay, router X is right here. All right, and you need to send data to W far on the network here. Okay, so you need to send data this way. Okay, now router Y and router Z. So these two nodes you know next to you because you're directly connected. So you get a report from Y saying, hey, X, I know a way to W. And Z says, nah, no idea. Okay, so what would you do passing data? Okay, do you pass it to Y or do you pass it to Z? Okay, so exercise your common sense and tell what that common sense say. Okay, so do tell Y. So let's go to the discourse space. Ah, I see. Yeah, because yeah, this is common sense, right? So let's see. Yunru Team 18. I would choose router Y as I think it's more important to make sure that I can get to the destination. I mean, hey, given the information there are, you pick the best one. You do the best you can, right? And between Y and Z, it seems that Y, at least Y knows the way, isn't it? I see. Makes sense. Choose Y because it's the only neighbor that has a valid route. Exactly. Well said. And Jaden? Yeah, you have many support here. Okay, really nice. Send the data to Y. Exactly. I guess you guys all choose Y, right? There, let me see if anyone dare to differ. Yeah, all of you say Y. Because Z just doesn't know, right? At all. So you see, you are a router. There are some adjacent routers to you that you can query. And you need to send the data to somewhere far away, right? So you just do whatever locally you know the best. That's the idea. Exactly, Ricky. Very good. Now let's move on to the second part. So this is quiz 42. And pick the next router, part 2. You're again router X, so still here, and you still want to send data to W. Okay, but this time, router Y says more, and router Z says also more. Router Y says, hey, I know a way to W. You want to reach to W, right? Hey, the pass cost is 3. So it's almost like 2 taxi drivers saying that, hey, you want to go to Taipei from the airport? Sure, I just need $3. And you and the other driver says $10. So which one would you pick? Y or Z? Again, Y. All right, so sorry guys, wait for me. Let's go to the discourse space. And this is channel W13, quiz 42. All right, guys, type it up. Yeah, so it's a little bit tricky, all right? So y says the cost to w is 3, but you know what? You have a cost to go to y. And so you might want to sum them up, right? So to y cost is 9, and y to w 3 together 12. And if you send it to z, the cost to z 4, and the past cost to w from z is 10, so 14. Let's see. Yeah, therefore, Stanley is saying, hey, comparing 12 to 14. Still, send the data to y. All right, very good. Because y costs less. Exactly. Yeah, exactly, Sherman. Very good. Yeah, because the overall cost is still lower, right? Very good. All right, and that takes us to yet another quiz. 43. Here, this is part 3. All right. So part 3 here, I'm still X, and I'm still sending to W. And there are two options, neighbor Y or neighbor Z, right? And the information they provided remain the same. Wait, but this time, somehow, you have some remote information, some semi-global information. Hey, there's a link between Y and Z, and the cost is 2. Okay, if you know more, not just the information locally. All right, what would you do? Pass the data to Y or Z or what? So in this case, would you pass it to Y or Z? And again, tell your common sense. All right, so this one might require a little bit of thinking. Let's give it 2 minutes. All right, so start counting time. All right, I see already. X, Z, Y, X, Z, Y, and then W, right? Because Y to W is 3. X, Z, Z, Y, 4 plus 2 plus 3. That's 9. That's better than 12, better than 14, isn't it? Very good. Very observant, guys. And hey, perfect solution. X, Y, X, Z, Y, W. That is the exact path, okay? Your traffic want to travel. Yeah, this is the least, isn't it? Very good. Because, hey, Team 9 formulate the answer a little bit differently. Hey, Z to Y. Hey, Z to Y is actually shorter if X, Z, sorry. Z to Y, I'm sorry. Yeah. I think Anthony meant to say from Z to Y, from Z. Hey, I think Anthony, you meant passing to Z because X to Y, the actual cost. So here, let me go to the Discord channel. Yeah, Anthony, I think you meant to say this, right? To pass data from X to Y, the cost is 6. From X to Y, the cost is now 6, which is better than going X to Y directly 9. Yeah, so X to Y should be 6 instead of 9 reported by Y himself. And you know what? Sometimes in local information routing, why might not know very well the best way, right, to go to X, unless Z tells Y something, isn't it? Good, but I see. Yeah, all of you get it. All right. Yeah, Sherman, marking the distance vector, marking the local routing. If it's this Dijkstra knows the best way is this. Yes. Exactly, guys. So with some additional information, regardless of the information provided by the neighbors, regardless of the information provided by the neighbors, neighbor Y and Z, because they are also making decisions locally, they might be misinformed, or there's some delay in collecting the information. So they tell something that's not optimum, then you make decision based on whatever you know. Okay, so this is local routing. If I ask you whether you like global or local routing better, I would say that some of you might have flipped, saying global routing better. All right, but let's not go that way and move on. To play this video, you see a little bit the spirit of distance vector routing that based on the local.
That should give you a rough sense how a router discovers a route without seeing the entire network topology. That is asking the neighbors to help. So neighbors will be reporting how they know about the destination. Now you know the neighbor's cost to the destination, and you know the cost for you to reach each of your neighbor. So that be X, and the cost from the neighbor to destination Y. You can calculate the sum of X and Y. If the value here is not infinity, you've discovered a route to the destination. But in order to discover the route that is the best to the destination, then you will need to check through all neighbors. Okay, for each neighbor, you find the cost to each of these neighbors. And you find out from that particular neighbor the cost to the destination. And you sum up, okay, X and Y for that particular neighbor. So you pick I such that Xi plus Yi is the lowest. There, you discover the best route, the shortest path. And I there is the next hub that leads to the shortest path to the destination.
All right, so that's distance vector routing spirit. And in a way, to communicate a little bit more, I want to say this. A router with limited perspective then perceive things also in a limited way. All right. So what I'm trying to show here for quiz 44 is this. We here see the whole picture, see the bigger picture. We see the object in the middle is an elephant. But the routers in distance vector are more like these scientists who are blindfolded, right? And you see the internet is huge, almost like an elephant, right? So these routers at some area in the network will only see things that are nearby. So for example, this scientist feel the tail and says it's a rope, right? And the scientist here on the letter, touches the trunk of the elephant. And it feels like what? A wall. So scientists with different perspectives would say things that would sound weird to us, to God. Similarly, routers in distance vector, they would know there are specific paths to a destination, but it might be odd. It might not be optimal to the God's eye. All right? Now, to exercise, okay, to convince you that your perception is limited by your perspective. Let's try to guess what is the item underneath the question mark. All right? So you're supposed to tell me what it is here. Good. Now, we invited several testers and they would give us some hints, okay, gradually. So first is, the tester says it's a drink. Something that you drink from a cup. Second tester, after drinking, says it's cold. And tester number 3, 4, 5 says, oh guys, it's sweet, soft, and chewy. So you guys, let's go to channel W13, quiz 44. As a router that gradually receive information from these testers, what do you think the item is underneath the question mark? All right, guys, yeah, you guys have 5 minutes. Okay. We're putting in it, all right. Something fancier. Boba tea. Ah, okay. Chewy. All right, guys. Yeah, I see you guys guessed bubble tea, or some sort of drink with jelly. Oh, there are more. Hello, hello. Oh, it's like a dessert. So maybe some sort of milkshake-ish type of yeah, dessert, right? Interesting. Do you have a picture of hello, Helen? That sounds interesting. By the way, James, the gummy bear sushi, could you, yeah, could you show a picture of that in case you can find one? All right, good. So you know what, guys? This is what Polly has in mind. Voila, the bubble tea. Yeah. Ah, I see. Yeah, bubble tea or the taro tea, or some sort of chewy jelly-ish stuff inside. I think one of the students said that cognac. Yeah, the Japanese chewy substance, right? Sweets. That looks good. Yeah. If you have a picture, please do. Yeah. And you know what, guys? From this quiz, I hope you see the behavior of the distance vector, behavior of the router in the distance vector routing. Yeah, it relies on information provided by the neighbors, which is limited in perspective. You see also that these perspective comes with some delay as well. Because the neighbors are also gradually learning to expand the perspective. And so we learn from them, we also gradually expand the perspective. Okay, so there's no optimality guarantee, there's no timely information guaranteed. At each time point, each router is trying to make the best decision there is locally. So distance vector routing is destined to be imperfect, okay? But it's gonna be what? Very low cost, isn't it? Oh wow, wow. I'm certainly hungry. James, thank you. Wow. Okay. Oh wow. Calvin, this is absolutely cool. Absolutely cool. Okay, I'm drooling. There you go. And guys, you know what? I think with the exercise from quiz 41 to 44, you get a sense of how distance vector behaves and how it's very different from Dijkstra, where you know everything and what you compute is the optimal. And the opposite side of link state or Dijkstra algorithm routing is that it's costly. N-square computation, and n-square bandwidth consumption, and n-square potentially memory space. All right? Good. And you know what? It's perfect timing, and I already borrowed 5 minutes because I know that this is going to take some time. But I hope that the idea of distance vector routing is well communicated. And next week, we'll start introducing distance vectors algorithm. All right? And I'll see you next week. Bye. Bye-bye. Guys, look at this. Wow. Yeah, I know there seems to be some delay before I see the pictures. Ooh, wow. Okay, bye. right, bye.